Hi everyone, and welcome back to another Langmuir Systems Fusion 360 tutorial video. In this video we'll be covering generating toolpaths in the CAM workspace, and then we'll cover simulating your toolpaths to see what the crossfire will do when you cut the part out. We'll pick up from the last video where we did the setup for the architectural plate, and we'll take a look at the front of this part here. Good. We'll take one more look at our setup, and then we'll start by creating a 2D profile cut by selecting the cutting icon in the top menu bar. This brings up the 2D profile cut dialog box, which contains all the options you can set and generate your toolpath. We'll get started in the Tool tab by selecting the tool we'll use to cut out this part. We'll select the tool that we created in a previous video, and again it should be saved in the local library there in the left section. So make sure you've got that selected, and we'll select our razor weld low amperage cutter and hit OK. Next, for cutting mode, we'll leave it as through auto. The crossfire doesn't have any internal quality settings, so you have to set the feed speeds, how fast the torch moves when firing, according to the cutter amperage, material, and material thickness. So next, onto the feed settings, we'll be cutting out 14 gauge 0.078 thick steel sheet and using the razor weld 30 amp plasma cutter at 30 amps. To find appropriate feeds for your cut, be sure to look at the cut charts for your plasma cutter. You can find our recommended feeds on our website's reference docs. We'll set all of our feed rates to 100 inches a minute for this part, and then we can move on to the next tab. I'll mention be careful not to hit the OK button until all the tabs are complete, or you'll get an error and have to restart. But let's move on to the Geometry tab. In the Geometry tab, we'll be selecting the lines to cut out. First choose Contour Selection, and then select the lines that we'll be cutting out with the plasma cutter. First the outside lines, and then all the internal holes here. As I do this, you'll notice the red lines appearing next to the selection. This is a reference to what side and direction the plasma cutter will be on and moving when you cut out this part. Remember that as the cutter is moving, it is removing material equivalent to the kerf width set in the plasma tool we set earlier. So which side of the line the cutter is on matters for pretty much all accurate part geometries. You can change which side of the profile the plasma cutter will cut on by clicking the red arrow. We'll keep these lines on the outsides of the outside profile of the part, but on the inside of any internal geometries like these holes. For small parts, you may need to zoom in pretty close to see which side of the profile lines you'll be cutting out on. When it comes to the direction of the torch travel, you should always cut counterclockwise inside and clockwise outside, but we'll get more into these later. Next, we'll move on to the rest of the geometry options. If you've got a complex part with multiple sketches, you can select the Select Same Plane Faces option, but we don't here, so we'll move on. We'll leave these settings on all loops and start outside, and we can skip tabs for now, as this part is big enough to fit across a few slats on the crossfire. In the Heights tab, you'll notice a number of different heights you can set. These are unneeded with the crossfire, as there is no Z-axis, and you can set your torch height manually. We'll just leave these as is and move on. In the Passes tab, we'll set a number of important options, the first of which is Tolerance, which determines how closely the toolpaths, moving in tiny linear motions, match the mathematical line. A smaller value here results in larger file sizes, and a larger one in smaller file sizes. This can be an issue for some programmed toolpaths, but this is a pretty simple one, so a tiny value like what we've got here is okay. Next, we'll select our sideways compensation, which alters the direction of the cutter movement as we discussed before. For most cutters, the best cutting side, due to the swirl ring torch construction, is the right side. This leads to the outside clockwise and inside counterclockwise cut directions. To do this, you'll choose the left sideways compensation. Next, we'll choose the in-computer compensation type, as we want to generate toolpaths that include the given kerf diameter and compensation. You can also select the Preserve Order option to cut out features in the order that you selected them in the Geometries tab. We'll keep the Stock to Leave option off unless you want to leave material around the outside of your geometry for a finishing operation like sanding or grinding. We'll also leave smoothing off too at the moment, but we can experiment with that later. So looks good. We'll move on to linking. In linking, we'll set a few critical parameters, the first of which is Keep Nozzle Down. The Keep Nozzle Down function maneuvers the torch around previously cut areas to avoid potential tip-ups while it's rapiding between cuts. So we'll activate the option, and that'll bring up a number of other options that we can set. As the Crossfire's torch doesn't retract, we want the torch to maneuver this way all the time. So we'll choose a large value here for max stay-down distance, like the length of the machine. The cut stock clearance, which is how close to the cuts we're willing to get with our torch, will depend on your cutter nozzle. If using some sort of shield, you'll want a larger value. I'll choose 0.1 inches here. We'll leave the force retreat off as it can't be done on the Crossfire. For the stay down feed rate, we're effectively setting our rapid speed, as the torch will always be down. The Crossfire can do 300 inches per minute rapids, so we'll set that as our value. For projects with a higher possibility of tip-ups or other problems, you'd be better served with a slower speed here. Next, we'll set our lead-ins. A lead-in is what allows for smooth starts in plasma cutting and other similar processes. The torch is fired away from the geometry and then moved towards the geometry along the cut line. This eliminates the possibility of any imperfections in the torch's firing from affecting the part's edges. We'll leave the lead-in selected, but turn the lead-out off. For our lead-in radius, we'll choose something small to fit within these holes, like 0.06 inches. For the sweep angle, we'll choose 90 degrees. We do this also because of the small holes in our part. We don't need any linear lead-in distance, so we can set that to 0. Note that you can only do this if you choose the in-computer compensation type. We'll stick with this value for the pierce clearance. And next, we'll select the entry point of the main cutout. I'll select a point along the flat here. That looks good. With all the tabs complete, we can hit OK to generate our toolpath. After the toolpath generates, you'll see it pop up in the browser window there, as well as seeing the toolpath lines in the drawing. You'll notice the rapid movements of the torch in yellow, the profile cuts in blue, and the lead-ins in green. This toolpath looks pretty good, but you'll likely want to simulate what's going to happen when you run the torch. You can do that by selecting the Simulate icon in the upper menu bar, and then hitting the Play button. This will simulate moving the torch head along the toolpath, and you can see where the tool will be firing and rapiding. And as you saw, it did the internal holes first, and then the outside profile. This looks pretty good, so in the next video we'll be moving on to post-processing this toolpath for Mach 3. Thanks for watching.